I am a structural and hydraulic engineer at the same time. Just wrap your heads around that. How is that possible? But, going forward, here are my supporters right here. It's my family right there and my 1.5-year-old. They deal with a lot of my model stuff and my model talk and everything. Here's my best supporter and then some right here. This is my golden retriever. He's 13 years old in this picture. This was taken this previous winter. And my son, he just loves to go around, jumping up and over him, and the dog just takes it. Very good dog. So, quick overview. Just go over the objective, project setting, and a couple more bullet points here. I'm going to try to limit some of the talk because I do talk too much, because I'm very passionate about this stuff. So, as you would suspect, the main objective was to analyze and evaluate the hydrologic and hydraulic conditions for this Maine DOT project in Freeport, Maine. The existing project consisted of a 50-foot clear span, and the northbound and southbound 92-foot, or northbound and southbound I-295 lanes consisted of 92-foot clear spans. We proposed to replace the bridge with a 107-foot clear span bridge. One of the main objectives, too, was to make the environmentalists pretty happy about this. Because if we replace a bridge and it acts as a constriction, you may change the hydrologic connectivity to the tidal marshes upstream and downstream of the bridge. So in some situations, that's the case. But as we get further along, we'll see how the proposed bridge actually impacts the tidal marshes. So you have Route 1 on your right, and then the 295 northbound lane on the left. And then you have a drainage ditch or swale in the center that fills up during the high tide. So here we are, we have kind of not even 10,000 foot view, but you get the point that it's a pretty complicated project. It's about 1.8 miles inland from the Atlantic Ocean. We have very wide floodplains here, about 500, 1,500 feet wide. Upstream of the crossings, you have the Pratt Brook and the Cousins River. Drainage areas are listed here. We also have a confluence upstream of the bridge, direct at a 90-degree angle too. And then downstream, so here are the crossings just to point them out. And then downstream we have the Royal River, confluence with the Cousins River, and then you can see where the mouth is with the Atlantic Ocean. So moving on, we're going to talk about the hydraulic analysis approach. Right off the bat, we want the 2D model. In my eyes, this was very complicated, and I didn't want to make too many assumptions about the characteristics of the tidal system. Just because of the multiple confluences and crossings, large tidal floodplain. So as a result, we use SRH2D. You may be saying, whoa, this is a tidal system. Why are we using this? Well, we're going to go into that. SRH2D neglects wind forces, wave motion, and the Coriolis effect. So this was appropriate for use because wind-driven waves are barely experienced here. You can see this in the picture in the slide. It's pretty flat. There's really not enough pitch for a wave to form during normal conditions. And then the Coriolis effect was not anticipated to affect the entire water body. It was deemed to be small enough where circulation patterns weren't going to be influenced by that. So that's why we use SRH2D. So the design considerations are from Maine DOT's Bridge Design Guide. Charlie Hepson's right there. He can talk to you more about those. He probably wrote them in there. So usually the steady flow cases are meant for scour analysis. You have the Q50 inflow typically with either a mean high water or mean low water elevation. For this case, we didn't consider a sea level rise because if you have a higher tailwater elevation, you have a lower velocity profile. And as a result, typically your shear stress will go down even though your depth is increasing. That's what I found here. So we're going to really look at the unsteady flow here. In particular, case 1. This is the model verification case where we'll talk about the calibration data we have, but typically that has an upstream low flow and a typical tide cycle down at the exit boundary condition. And then you got the other two cases here. So before you ever put together a model, you have to collect data. It's just the way we have to do things. So right off the bat, I got terrain data, which consisted of just regular conventional survey, no bathymetry, in conjunction with the as-built plans just to make sure that the cross-section of the bridge was surveyed correctly. To point out, when we got the survey, we found that the bridge was too wide. We didn't have vertical wall abutments, which you can see in this picture here. It's pretty small. We can zoom into it at a later time. And then also, I just want to point out that we had enough, we're modeling about like 2 to 3 miles upstream total from the Atlantic Ocean, and I only had to stamp a channel for 700 feet. Put that in perspective, only 6% of the Cousins River. So we have some pretty good data here, luckily. We don't always have that for every case. So on October 10th, about a year ago, we collected water surface elevations and velocity data at the bridge. We try to stay consistent at the downstream location, which is shown in the picture here. For hydrology, it's very hard to estimate freshwater flows for tidal systems, especially during a low flow condition. So we just use stream stats to estimate the October flow statistics. Got US Route 1 here, and then downstream, about 9 miles away, we have the Portland NOAA station. This collects water surface elevations every 6 minutes. And something that we need to account for is the geoid. Who here knows about the geoid? Okay, so the geoid is the true surface of the Earth. It's not fully smooth. It's based off, don't quote me on this, probably the mean sea level elevation. But the point being is that the Earth is not perfectly smooth. It's pretty rugged. So the station's only 9 miles away, but we had to increase the water surface elevations by 1,200, so 0.12 feet. That might sound a lot, but when you're calibrating a model, every 1/10 of a foot makes a huge difference. So here we have our data. So, oops, that was the mouse. So we have on the secondary axis, we have the velocity profile that we measured. USGS states that we should actually take 3 measurements in the water column. We can only take 2 because my broomstick wasn't long enough. So we had a velocimeter with us, or a flow meter, as some call it. So we tried our best to get the water surface velocity, and then we try to get mid-column as a consistent measurement throughout low depths and high depths. And then with the dandy tape measure right here, we got the solid square measurements. We had a known point on the bridge fascia. Bridge fascia is just another way of saying the curb. And then Charlie Hepson luckily installed some transducers upstream and downstream of the bridge, which is represented by this dotted line right here. And then here's the green solid line. That is the tidal boundary condition that we used. That's the adjusted NOAA station tidal curve. I just want to point out that there's about an hour lag between the ebbs. The ebbs, the low point or low tide, which is kind of significant when you're thinking about the lag from the Atlantic Ocean to inland. So, mesh development, we could talk all day about this. I'm sure Kevin can talk all day about this too. He had a very good presentation. But point being is, main channel, Dr. Lai suggested to use quadrilateral elements in the main channel. They're a little bit more efficient, they take up more area, less computation time. In the overbank areas, we have triangular elements. They take a little bit more computation time, but it gives a good marriage between the terrain. When you discretize the terrain, you're kind of losing some resolution just within itself. So what the triangular elements do is they give you a better representation of the terrain, but you shouldn't be using them everywhere because you're going to increase your computation time. Just excuse me 1 second. I got to get some water. Oh, it's right there. Never mind. So calibration. When we go through this, thank you so much. Does this count towards my 5 minutes, Scott? Okay. So going on, calibration. Again, I said freshwater flows are pretty hard to estimate. So in this model, it was a calibration term. Very hard to measure. We didn't have the budget to figure out what the flows coming in were every day through the bridge and measuring the precipitation too. But a main thing that we do in 2D models and 1D models is that we adjust the Manning's N in order to mimic the measured results or measured data. Something that I was lucky to do because of FHWA was come back to this problem. I started off with a budget from Maine DOT, got the project done, spent a lot of my own time getting the project done because it was a complicated project. But through the case study, I was able to come back and do a time step sensitivity analysis, mesh resolution, decreasing it, and then play with the model domain a little bit more too. So here you can see that the freshwater flows are pretty low. The 50 percentile flows for the Pratt Brook in the upstream Cousins River is about magnitude of 5 cubic feet per second. Very low flow. Royal River, around 140 CFS. Again, for a 140 square mile river, that's pretty low flow. So when we go look at model domain sensitivity, sometimes you have to put your boundary condition far enough away so it doesn't influence your model. But also, when you look at these two pictures, you can see that the small domain only encompasses the Cousins River and the Pratt Brook. Look at the large domain, it encompasses the Royal River and a small tributary. You can see in the picture on your right where the small domain limit cuts off. So, small domain, coming back, always thought more was better. We'll go to that later. Small domain had 79,000 elements. Large domain had 125,000 elements. So here are the results of the small domain solution. Used a 5-second time step. Again, secondary axis is the velocity profile at the bridge, and the primary axis is the water surface elevations. I didn't put the boundary condition here because it was just going to get too much fluff, and it wouldn't convey the information. But I just want to point out something. If you're looking at the rising leg right here, you can see that there's about a 0.3 foot difference in elevation, but also what this suggests is that there is not enough lag as the tide's coming in. There's not enough friction, there's not enough losses. So as a result, that's where the large domain came into play. When we go back and forth between the two, you could see that we have better correlation in water surface elevations, but I want to point out that the velocity profile remained the same for the most part. The ebb shifted a little bit. The ebb occurs when there's a zero velocity. That actually occurs in the field on normal conditions with low flow. If you have higher flow, that may not happen. So here's just a GIF image of a typical tide using the large domain solution. I just want to point out in some areas we have ponding, especially in the tributaries in general. That's just a high point in my mesh. I wasn't really too concerned because it didn't affect my solution too much. So I'll just give it a couple more runs for you guys to soak it in. And then I just want to point out one more thing. If you look at the Pratt Brook 295 crossings and Route 1, you can see that there are significant differences in the water surface elevations in the Pratt Brook versus the Cousins River Bridge. And similarly, upstream of the Cousins River Bridge, you can see that the Cousins River has a higher water surface elevation than the downstream elevation. You see white, that's a low elevation. You see dark blue, that's a high tide situation. So time sensitivity analysis, I should suggest this on any unsteady state model. I just want to point out, let me ask a question. Who thinks the time step will give you more accurate results? Very good. It does not. It's just a way to get better convergence. So if you don't have confidence in your model, you perform a time step sensitivity analysis, you get more confidence in your model, saying, my solution did not deviate from the previous time step. So, to put this in perspective, I ran a 10, a 5, and a 1 second time step. The 10-second time step diverged from solution. SRH2D crashed. 5 second converged, had a stable solution. No hot spots that influenced the solution as a whole. And then I went to the 1 second time step, and you could see here that there is really no difference at all in the water surface elevations or the velocity profile. Put this in perspective. With this domain, the 125,000 elements, a 5 second time step took roughly 9 hours on my computer, and then the 1 second took 15. So there's a huge jump in computation time. We're going to move on to mesh resolution. So being a green engineer at the time with two-dimensional modeling, it's like more is better. Let's try to represent the terrain as much as possible. So with the large domain, I use the 5-second time step for a 57,000 element mesh and 125,000 element mesh. Computation differences, to run a 24-hour period, 2 hours with the 57,000 element mesh, 9 hours with the 125,000 element mesh. I want to point out that I did not run every model 7 hours. Did not do that. What I had to do, though, when I was calibrating the model, I started far enough away on the tide curve where you get numerical convergence somewhere over here. It's just the process. I give a lot of kudos to Dr. Lai for doing that, giving a very stable converging model in general. The point being is I started the model at like 6 a.m. So what happened was it was like a level pool situation, and then we started getting convergence here. There was no deviation from the tide curve, and then the velocity profile started to converge. And that's how I started calibrating my model to make sure that the ebbs were matching. That was the more important part to me, was making sure that we're getting the friction losses correct. Something I want to point out here, only a 0.1 foot difference between the two models at that location in the tide curve. Pretty good. I can't complain about it. But again, I came back to the problem. I could start picking at it. So the proposed conditions, we used SMS. SMS was heavily used on this to develop the terrain, and as well as putting the proposed grading and layout to model the proposed bridge. So for Maine DOT project, we utilized the 125,000 element domain simply because I was under the gun, have a budget, and had to get results out there. And I knew that the results calibrated well with the measured results, so I didn't want to question it. I couldn't go back. 5-second time step was used, and you can see here what the proposed mesh looks like. So here the comparison. It's pretty hard to see the two water surface profiles essentially overlap with each other. And you can see that there's only half a foot difference at mid-tide, or half a foot per second at mid-tide here, which suggests that we're really not putting a huge influence on the tidal cycle, the influence on the salt marshes. That's what it's suggesting. There's other ways you can show this in SMS where you can subtract the surfaces from each other and see what those differences are from time step to time step. But for this presentation, I think this gets the point across that we're not really screwing up the system. So just from conclusions with a two-dimensional model, the 2D analysis allowed us to effectively calibrate and verify the results, as well as understanding the complicated system here. The results indicated that the replacement bridge did not significantly affect the flushing characteristics of the salt marshes. So tips and tricks, I borrowed this from Scott. I think it's great. Some shortcomings that I had were I didn't start big. I had to keep coming back. Start big. Locate. Don't try to shrink your model in a two-dimensional area, because here's the thing. It doesn't take much more effort in order to have a larger model. I'm not saying to increase your mesh resolution if you don't need to, but you can perform that sensitivity analysis in order to have more confidence in your results. Collect all the data that's available. Think about it this way. There's a lot of data out there, like NOAA, LIDAR is out there too, and just survey data. Something that I'll be working with Tim Mallet on and try to help out with is collecting bathymetric data using sonar. I think that's the next step for two-dimensional modeling. So when you're doing the data collection, collect aerial photos. What's that do? Remember earlier you saw the Royal River? My gut told me that that was going to influence the solution in some way, and it did. You can also look at the aerial photos to see if there's any hydraulic structures, such as dams or just downstream bridges that may affect the water surface elevations at your bridge. Collect field measurements where possible. I would say that depends on the risk of the project and the importance of it. So velocity is important for calibration, as well as the water surface elevations. Always perform a sensitivity analysis. Someone on the first day stated this, and I totally agree. Sometimes you get flows from stream stats, and they may not be right. Sometimes when you calibrate the modeling, use stream stats flows. I'm working on a Maine DOT project right now where the flows aren't calibrating well with the measured water surface elevations for a peak flow or a peak flood. Perform time step sensitivity analysis for unsteady state models. You don't have to do it for steady state, just for obvious reasons. And then, it's just data on mesh resolution too. Play with the mesh. It's fun, it's easy. Try to be efficient about it. So that concludes my presentation. Are there any questions?
Outside of the structure, was the, I know this is marine silts and clays, and I recall you had looked at shear stress as a model, but were there other morphological features that you identified?
Yeah. So it's a clay, silty soil here. You can kind of see it in this picture. This kind of sums it up. You have vertical walls. This overall, for now, we have a stable bottom. You would have, I'm kind of going a long way on this. You have a kind of a clear water condition through here because it's all clay, silty soils. But what the survey showed was that at that confluence of the Pratt Brook and the upstream Cousins River, just upstream of the 295 bridges, there's a 17-foot scour pool there. So because of the slope of that bowl, essentially, I had to add more elements. I don't know if that answered your question, but yeah, you don't want to have that was an important feature just to estimate the losses here. Charlie?
I don't know if you recall, what kind of roughness did you use for the high marsh surface?
That didn't really have an impact on the solution. I played with it from like 0.03 to 0.04 because it just did not affect the solution, the draining characteristics. It was more about the tidal boundary condition, had more effect on that. But in the model, I used 0.04, and in the main channels, typically I used the value of 0.018 to 0.02. And that was because of calibration. I started out with 0.03 and then just worked my way down because 0.03 increased the lag in the ebbs.
Other questions out here?
Did you use a sensitivity analysis on your time step?
I did. I'll show you. We'll get there. Right there. So the curves, the lines just overlap. There's not much difference between anything.